The probability of defective in this problem is 0.1. The probability of finding a good component is Q. So these are the characteristic of Bernoulli trials. And if we have the n trials, 10 trials, so we can have successes x variable as 0, 1, and in sets of 10 randomly chosen, we can have up to 10 defective components to appear in those sets, and their probabilities can be computed. So now today I compute the probabilities first by binomial expression. So we know how to compute it with the expression, and we can also compute these things with the software, the facility from Microsoft Excel. So here is a function, binomial dot distribution. So it requires the desired number. So I select the number 0. Okay. The number of trials, from here, the number of trials. So I have 10 trials. I can define it from the respective cell, $4. And then the probability in one trial. So by default, it should be the probability of success, which is at 1. And then whether you are going to generate cumulative probability or the probability mass function. So we have to set the final logical variable as false. False. False must be false. We have got one number, and we can repeat that one for the rest of calculations. Right. So see here these numbers, 10 out of 10, the probability goes to 10 raised to the power minus 10, right? So 10 raised to the power minus 7, 10 raised to the power minus 6. So it means the events with the greater number of defective components, they are very, very small, right? So like in journal sciences, we have with every measurement, we say these are the things that we can measure, and the rest are smaller than the least count of our system. We cannot measure them. So those errors in those ranges can be neglected and must be neglected if you come up with a design. Otherwise, you will never end up with a design, right? So it means the significant numbers are the okay. If you believe up to 6, these are significant numbers for this problem in 10 trials. If you increase the number of trials, so you may have the different kind of situation. So this is with the probability 0.1 and 0.9. Let's see the case of, and before that, let me plot it so that we can see everything in a vivid fashion. So I do the plotting. Not these two. Select data. Remove this one, add a series. And now the values. All 10 values have been selected. Vertical axis. And well, my numbers start from 0. So these numbers. That's great. So we have peak value somewhere here, right? peak value shifted to the smaller values. And if I compute the mu value for binomial distribution is equal to n times p. So n is b4. b4 times p value. So we see p value here. Mu value is 1. So if you see the peak is around the mean value, right? And the mu value is 1, whereas the variable goes up to 10, right? It means the majority of the events which are possible from practical point of view are the small numbers, right? And if you further reduce this number, for example, if I set that one to 0.01, 0.05, so then now you see that the number 10 to the power minus 6, it is further shifted to the smaller values, right? So peak is shifted further to the lower values, right? And let's do the contrary. If I set it to 0.5, so it is going to be a symmetric one, right? Now if I set the number to 0.05, the probability of success is very small, right? You have to carry out many trials to get the desired outcome, right? So we can do the estimation by using the Poisson formulation, Poisson expression. The Poisson expression requires the mu value to be computed, right? So now I compute the same probabilities with the Poisson expression. Poisson expression is believed to be the simpler calculation as compared to the binomial expression. So that was very true before the advent of calculators. However, with the softwares and by using the commands, you will never experience, you will never feel that kind of difficulty. So I'm here showing the Poisson. Poisson is the name of the French mathematician. So now the Poisson distribution is computed as let me use the formula function available from Poisson. So there is a similarity in using Poisson dot distribution. So it asks for 3 parameters: the value of x, then the mean value, right? And we have the underlying assumption that we are talking about rare events. The probability of success is very small. So the mean value, let's pick it from $4. So it has been rightfully adopted. The last argument is the logical one for cumulative or for the mass function. So I am looking for the mass function, false. So the number, and you can compute the probabilities. So you can see that the numbers are close, but seeing becomes believing science to generate the numbers. If you generate the error estimate. Error estimate, the problem was from binomial distribution from fundamental point of view. However, mathematically it can be computed by Poisson expression. So I say the estimated value minus the exact value. Okay, this is going to be the absolute error to this point, and let's stay with that one, and call it okay. This is fine with this absolute. So you have this much discrepancy in the estimation computed from Poisson distribution, right? So, and for higher values, the values are negligible. So you have fairly accurate values from Poisson distribution as well, right? So it means you can compute the binomial distribution characteristics by using Poisson distribution formula, which is to legendary mathematicians simpler than the expression of binomial distribution. You may have a different opinion in 2023.